At the rocket development facility in the windswept plains of Kazakhstan, huge metallic structures loom against the skyline. Each day, engineers perform final checks on the RD-180 rocket engines, a fusion of complexity and elegance. These engines are designed to generate over 400,000 pounds of thrust as they carry payloads into the velvet abyss of space, but what makes them particularly fascinating is the intricate dance of propellant within. Before this engine can unleash its power, a small fraction of its fuel must first swirl, twist, and spin at astonishing speeds. Why, exactly, do these colossal machines need to treat their fuel like a dance partner before the ignition? How does this seemingly superficial act reveal a deeper ingenuity woven into the very fabric of rocket science? Every rocket launch is a masterclass in overcoming gravitational forces and atmospheric pressures. But, in this dizzying ballet of physics, one might wonder, what is the significance of spinning the propellant before it ignites? Why do engineers design rocket engines this way, instead of opting for simpler combustion methods? The answer lies deep in the world of thermodynamics and the very nature of combustion itself. By the end of this journey through innovation and engineering, we will uncover the pivotal role that spinning propellant plays in maximizing efficiency and performance in the largest rocket engines on Earth. The mechanics of a staged combustion engine, such as the RD-180, can seem overwhelmingly complicated, but they serve a very specific purpose. The heart of this engine lies in its innovative use of a preburner, where a small fraction of the propellant, comprising roughly 20% of the total fuel, undergoes initial combustion. This preburner creates hot gases that drive the turbopumps essential for pushing the remaining propellant into the combustion chamber at staggering speeds, about 50,000 revolutions per minute. This dizzying velocity creates enormous centrifugal forces, ensuring that the propellant is atomized efficiently, maximizing the combustion surface area. Let's delve deeper into how these systems operate. Picture for a moment the propellant entering the preburner, where it is subjected to extreme conditions. The temperature can soar to over 3,000 degrees Fahrenheit in just seconds. But, engineers didn't stop there, they designed these systems to extract nearly all of the chemical energy locked within the fuel. This is key because, by pre-burning the propellant, the engine can achieve an incredibly high specific impulse, over 310 seconds, making it one of the most efficient engines operating today. So, why not simply combust all the propellant at once? Simplistically speaking, a gas generator cycle engine could achieve this, but at a substantial cost in performance. These designs typically waste a portion of the exhaust gases vented straight into the atmosphere, rather than using them productively. In contrast, by using a staged combustion cycle, engines like the RD-180 can reclaim that energy, allowing for more efficient thrust and minimizing wasted propellant. When comparing efficiency and thrust-to-weight ratios, it becomes evident that the staged combustion cycle is far superior. Consider the Space Shuttle's main engines, which operated on a gas generator cycle. They produced less thrust than the RD-180 while burning a larger amount of fuel unnecessarily. The RD-180, on the other hand, represents a culmination of decades of research and engineering. Its design is not merely a technical decision but a strategic one to push the boundaries of what rocket engines can achieve. Now let's visualize how the propellant behaves as it spins within the combustion chamber. Imagine dragging a heel downhill. As gravity pulls you downward, the friction generated between the ground and your foot can either slow you down or propel you further, depending on your motion. The spinning propellant behaves similarly. It experiences centrifugal force that spreads it out against the chamber walls, increasing the contact area for combustion. This method helps to ignite the fuel completely and uniformly, leading to a more stable and powerful thrust. Despite its advantages, the staged combustion system isn't without challenges. It introduces complexity in design, which requires precise engineering and extensive testing. Take the example of the Russian RD-170, a predecessor to the RD-180. Its four combustion chambers struggled with issues like combustion instability, leading to difficulties that ultimately resulted in extensive redesigns. The intricate nature of managing pressure and flow in multiple chambers is no small feat, yet the refined engineering lessons learned from those setbacks paved the way for the RD-180's more robust design. Which of these machines would you least want to be standing next to? The precision and delicate dynamics of rocket engines certainly make for a potentially hazardous environment. Yet, this is precisely what makes their effective operation critical. Understanding the fine balance between energy extraction and performance helps us appreciate the engineering marvels we send skyward. Now, let's consider a common misconception in rocket engineering. Many people assume that using more fuel translates directly to more power. However, the reality is entirely opposite. In a staged combustion engine, burning less propellant beforehand can yield greater thrust because it efficiently reuses exhaust gases that would typically be wasted. By carefully calibrating how much propellant is fed into the preburner, engineers can enhance the performance manifold, taking advantage of pressure and temperature differentials. So, here's the trick that ties it all together. Rocket engines like the RD-180 don't simply require combustion, they require finesse. By spinning a portion of the fuel prior to ignition, these engines capitalize on thermodynamic principles to unleash the maximum chemical potential. This intricate balancing act is where the real magic happens. The tangible result is an engine that doesn't just perform but excels, propelling spacecraft with incredible efficiency. As we draw closer to the end of our exploration, it becomes evident that the hidden engineering processes at work are both intricate and awe-inspiring. The staged combustion approach demonstrates how innovation lies in embracing complexity for the sake of efficiency. By finding ways to extract every ounce of thrust from propellant before it ignites, engineers continue to push the boundaries of aerospace technology, showcasing the ingenuity of human design. In the silence of the launch pad, as the RD-180 engines roar to life, they remind us that the machines moving our world forward are stranger than they appear. Each component, each decision, contributes to a larger narrative of exploration and human ingenuity. The machines that move the modern world are stranger than they look. Subscribe, and we will take apart the next giant together. As the RD-180 thrusters push the spacecraft into the air, the incredible intricacies of staged combustion become more apparent. One of the impressive figures associated with this engine is its thrust-to-weight ratio, which exceeds 180 to 1, a figure that propels it into the realm of elite rocket engines. This ratio demonstrates that for every pound of engine weight, it generates more than 180 pounds of thrust, making it a key player in space launches, particularly for the Atlas V rocket series. To understand the mechanics at play, let's focus on the role of the turbopumps in this engine design. Most rocket engines use turbopumps to move fuel and oxidizer into the combustion chamber. However, the RD-180 features two high-speed turbopumps that operate independently. This separation is a clever design choice that serves to enhance the engine's performance and stability. These pumps spin at an extreme velocity, enabling the efficient delivery of fuel at over 5,000 gallons per minute. These dual turbopumps, each capable of generating pressure upward of 800 psi, are driven by the gases formed during the preburner phase. This design is not just efficient, it is pivotal. Such high-pressure injection of propellant ensures the fuel is finely atomized. When the atomized fuel mixes with the oxidizer in the combustion chamber, it creates a finely tuned environment for combustion, significantly enhancing the uniformity of the burning process. Consequently, rockets that utilize this system do not only achieve higher thrust but maintain it with remarkable consistency throughout the burn cycle. The meticulous process of atomization cannot be overlooked. Consider the dense clouds of mist that form when a gardener uses a high-pressure spray nozzle. Just as that mist covers a wide area and ensures more thorough watering, the high-speed atomization of propellant ensures a maximum surface area exposure within the combustion chamber. This efficiency directly correlates with combustion stability, leading to predictable thrust output, a critical requirement for rocket launches where precise calculations dictate mission success. To further illustrate this, let's take a look at the Saturn V rocket, which famously propelled astronauts to the moon in the late 1960s. Its F-1 engines employed a gas generator cycle similar to the Space Shuttle main engines and suffered from the inherent inefficiencies associated with that design. The F-1 produced around 1.5 million pounds of thrust each, but a significant portion of that power stemmed from waste gases vented rather than fully utilized. In contrast, every droplet of propellant in the staged combustion engines, like the RD-180, is meticulously harnessed to produce maximum thrust, showcasing how the advancement in engine designs marks a leap in our ability to explore beyond our planet. Drifting deeper into the world of combustion, let's discuss the thermodynamics governing the preburner. In a standard combustion cycle, when fuel and oxidizer mix and ignite, we typically observe a surge in pressure and temperature. In a staged combustion engine, engineers exploit these thermodynamic properties to superheat the propellant gases before it enters the main combustion chamber. Let's visualize this. Imagine boiling water in a large pot. As the temperature rises, the movement and agitation in the pot increase, which can produce steam pressure. The same principle applies here. Superheating the propellant gas creates a high-energy flow, which directly enhances the efficacy and power of the main combustion phase. The use of staged combustion also offers an additional upside through its ability to minimize combustion instability. Combustion instability in rocket engines often emerges as a result of pressure fluctuations that can lead to violent oscillations, which ultimately harm the engine structure or, in worst-case scenarios, result in catastrophic failure. The design of the RD-180 minimizes this risk. Its well-calibrated preburner creates a stable gas flow, a crucial aspect in delivering consistent and reliable thrust. Engineering marvels aren't born in isolation, and the road to achieving the efficiency seen in engines like the RD-180 is paved with lessons learned from prior setbacks. The RD-170, its predecessor, faced a series of development hurdles as engineers tried to work through combustion instability and the challenges of managing multiple combustion chambers. The resolution of these issues has significantly informed the design of newer engines, highlighting a legacy of innovation built upon previous trials and errors that refine our approach to aerospace engineering. One significant historical example we can observe is the Russian N-1 moon rocket. This project, ambitious in scope, faltered due to combustion instability in its engines, which utilized a daunting 30 engines clustered together. The sheer complexity led to severe challenges when attempting to manage their individual combustion properties. Instead of a cohesive thrust stream, the engines created a chain reaction of instability that derailed the program. Such experiences cemented the understanding that soaring complexity could be detrimental, a hard lesson that shaped future designs like the RD-180 that employed more streamlined and manageable systems, leading to far fewer points of failure. As we continue to unpack these complex engineering marvels, let's take a step back to explore how the advancements encapsulated in the RD-180 and other modern engines influence our everyday lives. The technologies developed for space exploration create numerous advantages applicable on Earth. The precision in measurements and controls essential for the rockets ultimately drive enhancements in various fields, from oil and gas to renewable energy sectors, all benefiting from increased efficiency in combustion technologies. Now, let's return to our centralized question. Why do engineers design complex, staged combustion engines rather than opting for simpler combustion methods? The core reason is efficiency. The thermodynamic advantages gained, the maximized energy output, and the reduced waste contribute to a significant push toward more economical and reliable space travel. This is not merely a quest for performance, it reflects a broader narrative of harnessing energy within constrained boundaries, an endeavor all engineers and scientists embrace. But within this innovation, there lies another pitfall. With increased complexity comes a greater demand for precision in engineering execution. The emphasis on high-speed turbopumps, specially designed preburners, and well-calibrated fuel injections necessitates robust testing and iteration. Should the system demand an adjustment, the fallout can be extensive. Launch failures in rocket missions often underscore this. For example, the Atlas Centaur launch system faced numerous delays due to reworks in their engine designs, confirming that each ounce of improvement in performance carries a corresponding burden of increased scrutiny and engineering diligence. As we reflect on this complex ecosystem of rocket propulsion and the staged combustion process, consider the vast human ingenuity manifest in every design iteration. The RD-180 and its peers don't simply represent advancements in space technology, they embody the collective intellectual struggle towards optimizing efficiency and enhancing our relationship with gravity. In the grand tapestry of engineering history, every innovation builds upon those that came before, like threads woven into a fabric of knowledge that enriches our capacity for discovery. Each rocket launch is more than just the culmination of mechanical prowess, it is an expression of humanity's relentless pursuit of understanding the cosmos. Amid the noise of the launch and the fury of combustion, we glimpse into deeper truths about the physical world we inhabit and the careful calculations that underpin our endeavors beyond the sky. These machines, quiet in their nobility, reflect a dance of physics and innovation, bringing awe not just in their function but also in the intricate stories of perseverance and problem-solving they tell. As we conclude our exploration into why the biggest rocket engines spin their propellant, we're left with a profound appreciation for the invisible forces at play, those principles of thermodynamics, fluid dynamics, and fuel chemistry that allow us to journey beyond. The staged combustion method indeed triumphs over simplicity, encapsulating the essence of engineering, complex yet beautiful, efficient yet challenging. The machine